There's a mountain above your head, 2.5 kilometers of solid rock, as deep as the deepest mines on the planet. Imagine this mass above you, skyscrapers stacked one on top of the other in several rows, all of it pressing down. And you stand beneath it, in a narrow tunnel, and hear the rock quietly crack. The mountain presses. It wants to close. Every crack in the wall is its attempt to reclaim what was taken from it. And somewhere ahead, in the darkness, there is a section where the rock doesn't behave like rock. It flows. Slowly, like a thick paste, it compresses the tunnel from all sides and tries to crush it. People have dug a hole here, 57 kilometers long, the longest and deepest tunnel in human history. And this is how they did it.
Let's rewind time and figure out how it all really started.
Switzerland, the heart of Europe. This tiny country is sandwiched between Germany, Italy, and France. The entire continent's freight traffic, from north to south, passes through it.
And across the road stand the Alps, a wall 4 kilometers high. For decades, trucks have crawled through the mountain passes, bumper to bumper, switchbacks, ice, avalanches, traffic jams that turn the most beautiful slopes into an endless truck stop. And the Swiss had a daring idea. What if you didn't go through the mountains? What if you went right through them? Right through them, in a straight line, along a flat line at the very bottom. The idea was first sketched out back in 1947, but back then it was only laughed at. Experts were blunt. It was impossible. And even if it were possible, it would take 50 years, because no one had ever dug a tunnel of such length and depth.
Just imagine, until this moment, no one in the world had dared to build an underground corridor of such colossal length and at such dangerous depth.
And only in 1992 did the Swiss themselves hold a referendum and vote. Build it, we'll pay. For the first time in history, an entire country voted to bore through its main mountain. And the Swiss knew what they were getting into,
because this mountain had been dug through once before. Back in 1882, the first Gotthard Tunnel was dug here, also a record-breaking tunnel by the standards of that century. But the cost was horrific. Around 200 workers died during its construction. 200 people for one mountain. Landslides, explosions, poisonous gas, diseases in horrific barracks. Now, more than a century later, Switzerland was planning to traverse the same mountain again, deeper, longer, and, most importantly, safer. Technology had changed. The mountain had not.
But the laws of physics are inexorable. The mountain hasn't softened over time. It remains just as deadly and unpredictable as it was 100 years ago.
That's the engineering challenge. A typical mountain tunnel climbs up to a pass and then descends. The train climbs, loses speed, and burns energy. The Swiss wanted something different. A flat tunnel. A straight line at an altitude of just 550 meters above sea level, at the very base of the Alps. The world's first flat passage through a major mountain range. The train passes through the mountain as if it weren't there.
But there's a price to pay. To keep the line flat, the tunnel must go deep into the mountain. Really deep. 2,300 meters down. Now the numbers themselves. The main tunnel is 57 kilometers long, and if you add up all the passages, shafts, and underpasses, it's 152 kilometers underground. The maximum depth is 2,300 meters of rock above your head. And all this needs to be dug from both sides, facing each other, so that the two halves meet exactly in the middle of the mountain.
The slightest miscalculation, and the two teams would have missed each other forever in this solid rock. The project looked like pure madness.
Is to build it. And here the first question arises. How can they even dig a 57-kilometer-long tunnel? If they dig only from both ends, construction would drag on for decades. The solution is brilliant. The mountain is being opened up not at 2 points, but at several simultaneously.
Engineers are digging sideways adits directly into the mountain's body. And in one place, in Cedron, they're digging a vertical shaft down 800 meters. 800 meters vertically. They're lowering people, equipment, and cement down through it, and hoisting rock up. And now the tunnel isn't being dug in two places. It's being dug at several points simultaneously, in opposite directions.
This brilliant move saved years of work. But look at the monster they used to punch this path.
Meet the main hero of this construction project, the tunneling shield. And it's not a drill. It's an underground factory on wheels. Each machine is 450 meters long, almost the length of 4 football fields placed side by side. 2,700 tons of steel. At the front is a rotating head, 9.5 meters in diameter, studded with steel cutters. It spins at 6 revolutions per minute and bites into the mountain. There are 4 of these machines. Each is assembled from 90,000 parts.
See how it works. The head presses down on the rock and crushes it. The cutters break off chunks of granite. The rock falls down onto the conveyor and travels back out of the tunnel toward the exit. But the machine itself doesn't push off from anything outside. It has nothing to push against. There's only rock all around. So it pushes itself up from the inside. Special stops extend to the side and press firmly against the tunnel walls. The machine is locked in place. Hydraulics push the head forward. A meter is traveled.
The system relaxes, pulls this entire multi-ton machine forward, locks into the rock again with a death grip, and continues to bite further. This is how the mountain yields to humans, step by step.
But granite is still the easy part. The real nightmare begins when the rock ahead changes. The mountain isn't made of just one rock. Hard granite, brittle shale, and worst of all, fault zones. Crushed, loose rock. And that's where the engineer's hell begins.
In such zones, the rock, under the weight of the mountain, behaves like plasticine. It flows. It presses on the tunnel from all sides, slowly compressing it. The walls close in on you. The prepared passage begins to close itself. This is called extruded rock, and it's every miner's nightmare. How do you hold back a mountain that's trying to crush you? Here's the solution. The tunnel is made in 2 shells. Immediately after the tunnel, a layer of concrete is sprayed onto the bare rock. It grips the rock and prevents it from crumbling.
As soon as the drill exposes the rock, robots instantly spray it with a liquid concrete under insane pressure. It sets right before your eyes and holds the vault.
And in the most dangerous areas, flexible supports and anchors are installed that bite deep into the rock. The trick is this. The supports don't try to simply stop the mountain dead in its tracks. They allow the rock to shift slightly, relieve the tension, and only then do they stop. You don't fight the mountain head-on. You dampen its impact. And only when the rock has calmed down do you install the final concrete casing of the tunnel.
But the mountain has another weapon: water. The mountain is filled with water under colossal pressure. Break through the wall in the wrong place, and an icy stream will gush into the tunnel from a crack in the rock. This was the engineer's worst nightmare. If not a collapse, then water. A breakthrough could flood the face and stop the machine.
A water breakthrough is the engineer's greatest fear. The icy rush can flood the tunnel face in seconds and bury a multi-million-dollar shield here forever.
Therefore, the rock ahead is constantly probed with exploratory drilling, peering tens of meters ahead, searching for water-bearing cracks before the shield hits them. And those streams that do break through are intercepted and pumped out. Hundreds of kilometers of drainage pipes run through the tunnel, draining the water from the mountain day and night. The mountain weeps, but the tunnel remains dry. And in the most difficult places, the giant shield is completely powerless. Where the rock is too loose, or where complex interchanges and halls need to be cut, machines can't be used. So the old method, drilling and blasting, comes into play. They drill a grid of holes in the rock, lay charges, retreat, and detonate. The rock breaks off, is removed, and the cycle repeats. Meter by meter, by hand. About a fifth of the entire tunnel has been completed this way. The remaining 80% was gnawed away by machines. Two technologies, old and new, are gnawed at the same mountain from two sides.
It's hellishly hot in here. Without massive air conditioning, the air at the rock face instantly heats up to 46 degrees Celsius from the glowing body of the mountain itself.
It's also incredibly hot underground. The deeper you go, the hotter the rock itself. At a depth of 2 kilometers, the rock is so hot that without cooling, the air in the tunnel reaches 46 degrees Celsius. It's impossible to work in such a furnace. Therefore, colossal volumes of air are pumped down the 800-meter shaft. One of the most powerful ventilation systems in the world cools the underground labyrinth and allows people to breathe. Without it, construction would grind to a halt in minutes, and the work never stops. Not day, not night.
At the peak of construction, up to 2,400 people descend beneath the mountain. 3 shifts, around the clock, year after year. While Switzerland sleeps above, deep beneath the Alps, 4 steel monsters gnaw away at the rock without ceasing. And gradually, 28 million tons of rock are gnawed out of the mountain. So much rock that it could build several pyramids.
You'd be surprised, but tons of excavated granite aren't taken out. It's processed into concrete right here, underground, and immediately used to reinforce the new sections.
But this rock isn't dumped. That's what the engineers came up with. The crushed granite is immediately transported to underground factories, crushed, and turned into concrete. The same concrete that lines the tunnel walls. The mountain literally builds itself from within. But there's one moment in this entire construction project that has the entire country holding its breath. The collision. 2 teams are digging toward each other from opposite ends of the mountain. Between them are tens of kilometers of solid rock. They can't see each other.
They're driving blindly, according to calculations and satellite data, through 2 kilometers of rock. And somewhere out there, in the darkness, the heads of the 2 shields are supposed to meet. The billion-dollar question: how much will they miss? Now consider how it's even possible to drive a car blindly through 2 kilometers of rock and not lose your way. The satellite signal doesn't penetrate downhill. Therefore, the shield's position is calculated differently.
The surveyors had to perform a miracle, drop the coordinates down narrow shafts, and align a perfect laser thread for dozens of kilometers through the darkness.
Points from the surface are transferred down a vertical shaft, and then, inside the tunnel, a precise chain of measurements is drawn, point by point, tens of kilometers deep. The slightest error in the calculations accumulates with every meter, sending the car astray. Engineers recalculate the course again and again. The mountain even distorts the direction of a plumb line, and this too must be taken into account.
Essentially, 2 teams are aiming at each other across the entire thickness of the Alps, guided only by numbers. On October 15, 2010, the shield head pierces the final wall of rock. The light of one tunnel meets the light of another. Miners in orange helmets shout with joy, and engineers measure the miss. And there's a number that sends shivers down your spine.
Fantastic precision! To drill 30 kilometers under the Alps from different sides and meet with a margin of error just the width of a palm.
Horizontally, the 2 halves diverge by just 8 centimeters, and vertically by 1 centimeter. 1 centimeter for 57 kilometers through the mountain. It's one of the most precise misses in the history of tunneling. They'd gone 2,000 meters underground, blind from both sides, and missed by a hand's breadth. But this triumph came at a price. Cutting through Europe's largest mountain doesn't come without a price. 9 workers died underground during the years of construction. Every kilometer of this tunnel was built by thousands of people, toiling in heat, darkness, and under the pressure of the mountain.
And that's worth remembering as you drive through the Alps in a matter of minutes. The tunnel is finished. But the tunnel isn't a railway yet.
Further up the mountain, tracks are laid, overhead lines are installed, ventilation, sensors, and safety systems are installed.
Before the first passenger train is launched, this incredibly complex safety system will be tested thousands of times, down to the smallest sensor.
There are 2 separate tubes, one for each direction. And between them, every 300 meters or so, crossovers, emergency exits, have been drilled. If something happens in one tunnel, people escape through the door into the adjacent tube to safety. Deep inside the mountain, approximately 1/3 and 2/3 of the way through, there are 2 underground emergency stations. These are rescue hubs right in the depths of the Alps. If a train runs into trouble in the middle of the mountain, it can stop right here, and passengers are evacuated through protected passages while powerful ventilation removes the smoke. An entire rescue system hidden under 2 kilometers of rock.
Everything is thought out to the last detail. The tunnel's safety will be tested thousands of times before the first passenger train is allowed through. In 2016, the Gotthard Base Tunnel opens.
The flow of trucks has moved from dangerous winding roads underground. No more traffic jams and blizzards, just clean Alpine air and absolute safety.
17 years of construction. And here's the amazing thing. The project was completed on time and on budget. $12 billion. For a mega project of this scale, it's practically a miracle. While other countries missed deadlines for years on construction projects 10 times smaller, the Swiss have completed the entire mountain and met the deadline precisely, strictly, Swiss style. Now look at the results. The train flies into the mountain at one end and out the other at over 200 kilometers per hour. What used to take trucks hours on serpentine roads now takes 20 minutes. A smooth, flat, straight line through the heart of the Alps. Freight has been moved from dangerous mountain roads underground. Fewer trucks on the passes, fewer accidents, less exhaust fumes over the green slopes.
An entire continent has become closer because one small country refused to go around the mountain and decided to go through it.
But piercing a mountain is only half the battle. What if you challenge the ocean and build an airport right on the water, knowing it will start sinking from day one?
And these aren't just nice words. Here's what's changed in the numbers. Previously, about 180 freight trains a day passed along the old mountain route. Now, it's almost 260. Longer, heavier trains run along a flat line, without climbing. The journey from Zurich to Milan has been shortened by almost an hour, and thousands of trucks that used to smoky over the Alpine passes have moved underground, onto the rails. Fewer trucks above means cleaner air above the slopes, fewer accidents on the switchbacks. A single straight line at the mountain bottom has relieved congestion in an entire region. That's the whole point. The mountain that divided northern and southern Europe for thousands of years wasn't torn down or circumvented. They simply drove right through it, straight down to the very bottom. The engineers didn't argue with the Alps. They carved a straight line through them and made trains fly where trucks had once stalled. Meter by meter, calculation after calculation, how do you keep something above water that, by all rights, should sink? That's for next time.
See you at the next impossible structure.